An ARM processor doesn't just run in one single state, it operates in several different modes. Think of these modes as different levels of authority or different contexts for executing code. The fundamental reason for this is to create a secure and stable system. The most important distinction to understand is between privileged and unprivileged modes. You can think of it like user accounts on a computer. A standard user account is unprivileged. It can run applications, but it can't change critical system settings or access other users' files. An administrator account, on the other hand, is privileged. It has full control over the entire system. In the ARM world, we see this separation clearly. At the bottom of the table, we have user mode. This is the unprivileged mode, designated as PL0 or privilege level 0. This is where almost all of your applications and operating system tasks will run. Code running in user mode has restricted access to memory and system resources, which prevents a buggy or malicious application from crashing the entire operating system. All the other 6 modes are privileged modes, at PL1 or privilege level 1. Code running in a privileged mode has full access to the system. This is typically reserved for the operating system kernel and other low-level software that needs to manage hardware directly. Now, most of these privileged modes are also called exception modes. An exception is an event that disrupts the normal flow of program execution. It could be an error, a signal from a hardware device, or a deliberate request from an application. When an exception occurs, the processor automatically switches into the corresponding exception mode to handle it. Let's look at them. Supervisor mode, SVC. This is the main mode for the operating system after it boots up. It's also the mode entered when an application in user mode needs the OS to perform a privileged task, like reading a file. The application executes a supervisor call instruction, which triggers an exception and puts the processor into supervisor mode to handle the request. IRQ, interrupt request, and FIQ, fast interrupt request. These modes handle interrupts from hardware devices. An IRQ is for general, normal priority interrupts, like a network card receiving a packet. An FIQ is for high-priority interrupts that need to be handled with very low latency, like a critical timer in a real-time system. Abort mode. The processor enters this mode when there's a memory access violation. For example, if a program tries to read from an address that doesn't exist or write to a protected area of memory, an abort exception is generated. Undefined mode. Undef. This is for when the processor encounters an instruction it doesn't recognize. This allows the system to handle or emulate instructions that aren't supported in hardware. Finally, there's system mode. It's unique because it's a privileged mode, PL1, but it uses the same set of registers as user mode. This is useful for certain OS tasks that need privileged access but don't need to respond to an exception. It avoids the overhead of switching to a different register set. A key point is that each of these modes can have its own stack space and a different subset of registers. This isolation is critical. When an exception occurs and the processor switches from user mode to, say, IRQ mode, it can use a separate set of registers without corrupting the state of the original user application. On the next page, we'll see exactly how this banking of registers works. This diagram shows us a really clever feature of ARM processors called register banking. It's all about how the processor manages its registers when it switches between the different operating modes we just discussed on the previous page. On the left, you see the register set for the user mode. This is the standard view for a regular application. We have our general-purpose registers R0 to R12, and then the special ones. R13 is the stack pointer, R14 is the link register, and R15 is the program counter. Below them is the CPSR, the current program status register, which keeps track of the processor's current state, like condition flags. As the text says, all these general-purpose registers are 32 bits long. So, What happens when an exception occurs, like an interrupt, which we call an IRQ? The processor needs to pause the user application and jump to run some special code called an exception handler. If the handler just used the same registers as the application, it would overwrite the application's data, which would be a complete mess. This is where banking comes in. Instead of forcing the software to manually save every single register to memory every time, the hardware provides private, or banked, copies of certain registers for the exception modes. Take a look at the columns for IRQ, undef, abort, and SVC. You can see they each have their own R13 SP and R14 LR. This means when the processor enters IRQ mode, for instance, it automatically switches to using a separate stack pointer and link register. This is incredibly efficient. The handler can immediately use its own stack and store its return address without corrupting the user's R13 and R14. You'll also see an SPSR register for each exception mode. SPSR stands for Saved Program Status Register. When an exception occurs, the processor automatically copies the contents of the CPSR into the SPSR of the new mode. This is crucial because it saves the state of the program that was interrupted. When the handler is finished, it simply copies the SPSR back to the CPSR to resume the original program exactly where it left off. Now look closely at FIQ mode. Do you see a difference compared to the other exception modes? FIQ, which stands for Fast Interrupt Request, has even more banked registers. It has its own private copies of R8, R9, R10, R11, and R12, in addition to its own R13 and R14. Why do you think that is? It's to make it fast. With these extra banked registers, the FIQ handler has several registers it can use immediately without needing to save the user's R8 to R12 onto the stack. This reduces memory access and makes the response to a fast interrupt extremely quick, which is vital for time-critical operations. It's important to notice that registers R0 to R7 are never banked. They are always shared across all modes. This means an exception handler must be careful to save and restore these registers if it needs to use them. Finally, there's that small note. System mode uses the user mode register set. This tells us that system mode, even though it's a privileged mode, operates with the same set of registers as user mode.